Okay, so really quick, we're going to do power functions when the exponent is a fraction. And so I know so many of you love fractions, and remember that these are also called rational exponents. And so really quickly to review, remember that when I have a rational exponent or a fractional exponent, like x to the 1/2, x to the 1/3, x to the 1/4, x to the 1/5, I can translate these into radical form. So x to the 1/2 equals the square root of x. X to the 1/3 equals the cubed root of x. X to the 1/4 equals the fourth root, and then x to the 1/5 equals the fifth root of x. But what about if it's not simple, like 1/2, 1/4, 1/3, 1/5, whatever? What if it's not that simple? Like, for example, if I have f of x equals x to a certain number over another number, or f of x equals x to the m over n. Well, remember that this is known as my exponential form. So when I write it out as an exponent, this is my exponential form. But I can rewrite this as f of x equals x to the m to the root of n. So remember that I can rewrite this as x to the m to the n root. And that when n is even, so when n is even, I can only have positive x values. So x is greater than or equal to 0 in these cases, because like if I have even this, the square root of x to the third, because I'm taking the square root of it, I can only have positive values in there for x. So if I have a negative value in there, my whole thing will be undefined. And so this is really important to remember. When n is even, I can only have positive x values, so my domain is restricted here to x is greater than or equal to 0. And so this is my exponential form again. This is my radical form. So writing it with radicals. And I am hoping that you guys are super psyched to be back working between fractions and radicals. And we're not just going to be going back and forth like we were before. We're actually going to be graphing them now. And I'm thinking that I'm probably going to have you guys using Desmos and your graphing calculator for a little while until you get comfortable. But before we do that, I hope you all have written this down. If not, pause the video really quick, write this down, and then we're going to start again. So pause it if you haven't written it. So I just want to do a couple examples of what I'm talking about when I'm going from exponential to radical form. So for instance, if I have f of x equals x to the 5/2, what that means is that my radical form will be f of x equals x to the 5th, the square root of x to the 5th. Because this is the same thing, I can rewrite this as x to the 5th to the 1/2. Because remember my power rule, when I have a power raised to another power, I multiply, and 5 times 1/2 gives me 5/2. So I can rewrite this as x to the 5th to the 1/2 power, or the square root of x to the 5th. So these are just examples I want you to write in the column of your note sheet, just so that you can have some familiarity between going back and forth. So another example could be, let's go from exponential to radical again. F of x equals x to the 2/5. So take a quick second and try and figure this out on your own. We're going into radical form. So what is my radical form? So this is exponential form. This is radical form. What is my radical form of x to the 2/5? So because I can rewrite this as x squared to the 1/5 power, my radical form will be the fifth root of x squared, would be how I would write that in radical form. So if you haven't written this down, pause the video and write this down really quickly. I'm going to erase the bottom, and we're going to go from radical to exponential. So pause it if you haven't written it. Okay, so if I have things in radical form, so let's say I have f of x equals the cube root of x to the fourth. Well, I can rewrite this as x to the fourth to the 1/3 power, because x to the fourth here is being raised to the cube root, or the 1/3 power. And then when I multiply those out, it becomes f of x equals x to the 4/3. What if I have something like f of x equals the fifth root of x cubed? Well, again, I can pull this out as x cubed as like the stuff under the radical, and I'm raising it to the 1/5 power. So it becomes f of x equals x to the 3/5. So I'm taking x cubed and I'm taking the fifth root of it. So for your homework, I'm going to have you, or for classwork, I'm going to have you do several practice examples of going between exponential and radical form just to be comfortable with it. And so I want you to pause the video and I want you to go through your practice sheets on converting between exponential and radical form. So when we are graphing, these rational exponents, these power functions of rational exponents, we're kind of going the same way, like that. We're using the same rules that we were with normal power functions. So we're doing the same kinds of things that we were doing before. The positive coefficient, like we're still having a coefficient and a power. So it's the same thing, ax to the n. But now we're putting in fractions. So don't be afraid of the fractions. If you prefer them in radical form, I also wrote the functions here from your guided note sheet with examples. And so what I'm wanting you to do with these, I'm going to go through example 1, 2, and 4. And for 3 and 5, I want you to do 3 and 5 on Desmos for homework and fill out the identifiers. So your homework will be the exponential and radical form, going back and forth between those, converting between those, and numbers 3 and 5 on this guided worksheet. So in number 1, we have f of x equals x to the 1/4, or I can rewrite that as f of x is the fourth root of x. And so if we remember our parent function, I'm going to use the parent function of x squared because these are my even exponents, like the x squared, x to the 4th, x to the 6th, the even exponents. My parent function looks something like this, where because my n, or my 1/2, my n value is even, I know my y values have to be greater than or equal to 0, because x cannot be less than 0 or the function would be undefined. And it looks something like that. It might be a little bit flatter than that, like that. And so when I'm raising something to the 1/4 power, like for instance, if I was to raise 2, or let's do 16 to the 1/4 power, the square root of 16 is 4, but my fourth root of 16 is 2. So my y value here is less. So my y values are generally smaller than my x then my x to the 1/2 or my the square root of x values would be. So where the square root function, parent function, would look like this, my y values for the 1/4 or the 4th root function are going to be smaller. So this is actually going to be a flatter function. So it's still got the curve to it. My y values are still greater than or equal to 0, but I've got a much flatter slope. And so for my domain, because my domain values are the ones that are restricted here, so I can't have x has to be greater than or equal to 0 here. My range, y is greater than or equal to 0 here, so I can see this here. X is greater than 0, y is greater than 0. My increasing interval is from 0 to infinity, so I don't have anything from negative infinity to 0, but I am increasing from 0 to positive infinity. If you can see that there. I don't have a decreasing, like I said, so the decreasing, there's none. My symmetry, there's none. My discontinuities, there's none. And with my end behavior, this is where it starts getting different, is when I have my domain restrictions. So you saw the end behavior was a little bit different with the reciprocal graph, and the same is true for my rational exponents. So my end behavior, as x approaches infinity, so x is approaching infinity here, f of x or y is approaching infinity. But I don't have an x approaching negative infinity. The greatest, or the less number, the minimum, the minimum number for x, or the minimum value for x, is 0. So x can only approach 0. So as x approaches 0, f of x also approaches 0 here. So that's my end behavior for this first graph. So again, what I want you to be, what I'm expecting you to get from this is not a perfect graph. I want you to sketch it. I want to see that because my function values, or my y values here, are smaller than my square root function, I want to see a flatter or something closer to the x-axis, a graph that's closer to the x-axis. I want you to show me that you know that there's domain restrictions. So because it's an even n number, so remember this is my n number here, because n is even, my domain has to be greater than or equal to 0. And then because my domain is greater than or equal to 0, my y, and I don't have a negative coefficient, I have a positive coefficient, my y value is also going to be greater than or equal to 0. I want you to show me that there's an increasing interval, no decreasing, no discontinuity, no symmetry, and then the end behavior, I want you to start to be able to identify that sometimes a graph doesn't always go to negative infinity or positive infinity, as we'll see in some examples. So in number 2, we're taking 1/2 x to the 1/5 power, or I can rewrite that as f of x equals 1/2 times the 5th root of x. And so this is similar to my parent function of the cube root of x, which the cube root of x, if you remember from your graphic organizer, looks something like that. It's a little flat, it extends to negative infinity and positive infinity, and it's kind of close to the x-axis. So similar trend to the one above, because it's a smaller fraction, so this is equal to x to the 1/3, because 1/5 is smaller than 1/3. When I put in numbers for x, I'm going to get a smaller y value here than I would for this 1/3 function. So I'm going to be compressing it vertically. I'm going to be making it flatter and closer to the x-axis. So my y values are shrinking, which means that I'm getting closer to the x-axis. I also have a vertical compression here by 1/2. So it's going to be much flatter. And I don't have a translation left or right. So what I'm going to do here is I'm just going to draw a flat graph, a flatter, odd fractional or rational exponent graph. So it should look something like that. Because my n here is even, or my radicand is odd, it's not even, I can have all real numbers as my domain. So my domain isn't restricted here because remember when I take the third root of something or I'm taking the cube root of something, I can have negative numbers for x. Like the cube root of negative 27 is negative 3 because negative 3 times negative 3 times negative 3 gives me negative 27. So my domain here, as you can see, is all real numbers. My range also, even though it looks really flat, is also all real numbers. It'll take a long time to reach positive and negative infinity for y, but it'll get there eventually. And then my increasing interval, if I look at my graph reading my interval left to right, I'm only increasing in y values. So my increasing interval is negative infinity to positive infinity, and I do not have any decreasing. This graph is nice because I have some symmetry here. So because it is an odd function, it is an odd power, and I don't have any domain restrictions here. So if this didn't have any domain restrictions, I'd probably have y-axis symmetry because it's an even power. But because I have domain restrictions for this, I don't have any symmetry. But for this one, I do. So because it's an odd power, I have origin symmetry. And then my end behavior follows the same rules of positive coefficient, odd power. So as x approaches infinity, f of x also approaches infinity. And as x approaches negative infinity, f of x also approaches, let's see if I can write this, negative infinity. Those look like 8s, but those are infinity signs. So this would be the graph that I'd have for number 2. And the information. And again, I don't want you to find intercepts or anything like that. We're just sketching and getting comfortable with drawing these rational, sketching these rational graphs, these rational exponent graphs. So number 3, I want you to try on your own. So try on your own. This one is negative 3 x to the 5 halves. I rewrote it as f of x is equal to negative 3 times the square root of x to the 5th. Or you can simplify it even further. Remember from our first unit we did on simplifying radicals. You can simplify it to negative 3x squared times the square root of x. So try that one on your own, and you can use Desmos, or you can just sketch it, and then do my identifier describers, like domain range, increasing, decreasing, symmetry, that kind of jazz. All right, the last one that we're going to do together is going from radical form into exponential form. So I'm graphing from radical form. So in number 4, I have negative cube root of x squared. So I'm taking the negative cube root of x squared. Let's see if I can actually write this out so you can see it. And so this one is a little bit tricky. So because this is the first time I have a negative here, my range restrictions are now no longer there. So my domain restrictions are no longer there. So I'm raising it. I have a radicand that's odd, so I no longer have domain restrictions. And I've got an x squared in the bottom, so I am going to be able to have, I am only going to be able to have positive numbers here, but then I have a negative sign, so this will make it so that my y is less than or equal to 0. And I know I just went totally roundabout on that, so I'm going to repeat that. So because here I have an x-axis reflection, and I have an x squared under a cube root, I would normally, without that negative sign, only have positive y values because I'm raising any x value now. I'm raising any x value to the second power, so normally it would just be positive, only positive. But because I have this negative sign, all my y values are going to be less than or equal to 0 because I'm taking -1 and I'm multiplying it by only being able to have positive numbers. So I'm only now going to be able to have negative numbers because of this x-axis reflection. And because this is odd, so n equals odd, my domain is all real numbers. So I can have any number here for x. So I can have any negative number because it's not going to be undefined because I'm taking the cube root, not an even root number. And I rewrote it out from radical form into exponent form, so negative x to the 2/3, because graphing it in this form is a lot more challenging, especially on your graphing calculator, than graphing it in an exponential form. And so if you're comfortable with this form, that's great. If you're comfortable with this form, that's great. I just want you to start being able to recognize the patterns that be here. So we have our domain, we have our range, and we're going to start graphing now. So this slowly comes down like this slowly comes down like this. You're more than welcome to use Desmos if you need to be able to graph this. These should be totally even, but given my amazing art skills, it's a little challenging for me to show you exact symmetry. But that's what your graph should look like for number 4. And so because this is, because I'm raising x to a 2/3, because I'm raising x to squared, really in here, this is under the radical, my symmetry, it's about the y-axis. So my symmetry here is about the y-axis. And if I look at this, I do have both increasing and decreasing intervals. I'm increasing in y from -infinity to 0, and I'm decreasing, reading left to right along my x-axis, I'm decreasing from x equals 0 to x is less than infinity. I don't have any discontinuities, DC, none. And then my end behavior here, because I have a negative coefficient and a positive and a even exponent here. So I'm going to have, as x approaches infinity, f of x approaches -infinity. And as x approaches -infinity here, f of x approaches -infinity. So following those rules and looking at my powers that x is being raised to, that would be how I would come up with that graph. So again, I want you to try number 3 and number 5. Number 5 is definitely a challenge. So number 5, try on your own. Something that looks like this: f of x equals the square root of 27 minus x cubed. So use Desmos, use your graphing calculator. I want to see some sketches. I want to see some descriptions. And please submit through Canvas so I can check those out while I'm on the road. All right, thank you.